Okay, good morning, everyone. My name is Maz Barami. I'm heading up educational program and outreach at Wolfram Research, also leading our quantum initiative. Our main product as of now is a collection of functions helping you to do any sort of, quantum computation in finite dimensional Hilbert space. And we call it Wolfram Quantum Computation Framework. The main reason that we call it quantum computation is mostly because it's not only about quantum computing. It's basically anything that you can do in a discrete Hilbert space, it's doable, in our framework. So it's much more than quantum computing. It's a packlet. So the first thing that you have to do is to install that packlet. There are two resources. The one that is basically deploy public is the first one, Wolfram, quantum framework. You can just, packlet install and you can get the framework, or you can use this link. The main benefit of this link is that, on daily basis, me and Nick, we are the main developers of this packlet. We update that if any bug or if new features, such as new visualizations and etc. So, and also whenever you are working with our packlet, if you notice any issue or any question, feel free to reach out to us, quantum@wolfram.com. Okay, so we had lots of discussion together with Nick, what is the best way of, representing our framework. So for this, tech conference, we decided to go in the reverse order. Usually whenever we talk about, our framework, we start with quantum basis, then quantum state, quantum operator, measurement. At the very end, we discuss about quantum circuit operator. But it seems like, that's the most popular function in our framework. So I'm just going to go ahead and start with quantum circuit operator. Our quantum circuit operator, as the name implies, that's the function you're going to use to build any quantum circuit. The patterns that you have to remember is like this. Either you are going to give it as an argument, as an input, a list of operator, or you are going to use a collection of named circuits that we have in our framework. Okay, so that's the very basic idea of how to use a quantum circuit operator. As the name implies, it's an operator. Basically, you can see it as an operation, a feature that can transform quantum states. So whenever you want to apply it on a quantum state, in case if you don't care about the detail of the quantum state and you want to go with register state, meaning that all the quantum states are in the ground state, that's how you can just apply it on your register state. Behind the scene, our framework understands the dimensionality and etc. Why I'm mentioning that, another reason in our framework, it's not only about qubits, it's not only about two-dimensional quantum system. Your quantum system, it can be in any dimension as far as it is finite. So let me just show you a few examples. So I'm just going to bravely go ahead, evaluate all of these, and step by step, we are going to go through them. So one way of, creating a quantum circuit is to go through some named operator that we have. The notation that we use, very similar to the same design that we have in Wolfram language, as close as possible to the way that we talk about operators in quantum mechanics. So I guess all of you can guess that what we have here is basically, a Pauli X operator, and we represent it by X. If you give it as a string of X, Y, and Z, what you see here is basically a collection of operators on different qubits. Those of you who are familiar with the circuits, each horizontal line represents a quantum wire representing a quantum state. The tagging that we use, the top one is your first quantum system, and it goes down. We start from 1 through 3. Remember that in some other frameworks, they start from 0 to n-1. Sometimes they put 0 at the bottom, but that's the notation that we have. And all of this representation, you can customize that. If you don't like it, you can change that. And what I did here, I just basically if you evaluate that, the object that you see is your quantum circuit operator. It has a summary box and etc. You just can ask for the traditional form. And that's the circuit that you see. So that's one way of, visualizing that circuit. Or you can just when you evaluate that, just, on Mac is Command-Shift-T for the traditional form, or you can directly here ask for the diagram. Okay, all of them are different possibilities. Okay, So that's one way of defining your circuit. Another way, it's very important, when you are designing a circuit, you would like to say, look, this operation goes on the second system. This operation goes on the third system. So it's simply we go it like this, your operation, and then you can specify what qubit you would like to apply it, or what qubit, it's better to say qubit. So as you can see here, in this circuit, we are saying nothing on the first system. The second system, apply poly X. So that's how you can basically specify that. A fancy way of doing that, I'm going to show it later, is adding operator explicitly, but your code will be much longer. This is basically the shorthand representation of your circuits. Let me show you a few other examples. For example, let's read this one. So we are saying that poly X applies on the second system. Hadamard, whenever there is no argument, it means by default the first one. So either you can say on the first one, or if you don't say it, automatically we would set it on the first one. And then poly Z on the second one. And if we look at the diagram, let's look at the diagram. As you can see, Hadamard on the first one, then X on the second one, and of course Z. And the order is the same order as you define it in your input. For example, if I just change Z and X, you would see that it applies Z first and then X. Remember, the order of operation by convention is always from left to right. So it means this one applies, Z applies first, and after that X, and etc. So the time goes from left to right, in a circuit diagram. We can have a big collection of conditional operation. The famous one is C0. So as you can see, it has a control target, and by default, what we are doing here, we are setting the first one as the control and the second one as a target. Of course, you can change it whatever way you would like. For example, here, let's read it. I'm saying C0, and then I'm saying that the control is the second one and the target is the first one, and it's like a flip version of a C0. Okay. Some people, they prefer visualization. They can understand visualization. Some people they can read it as it is. I don't know which way you understand it better. But at the end of the day, using the common language for the circuit, a circuit is a collection of gates, a collection of operators. The way that you should see a circuit is an operator composition. That's literally the way that we're defining our circuit. For example, look at this case. So what we have here, we have poly X on the second one, Hadamard on the first one, and Z on the second one. And if you look at for the operators as the property of that circuit, that's literally the collection of operators for that quantum circuit operator. So behind the scene, what's happening is that you have this collection of operators, quantum operators, and you create a composition of these operators, and one by one in a sequence, you are applying that on your quantum system. So that's why, whenever we talk about, circuit operator, I always tell our, users, see it as an operator composition. You are constructing an operator composition. So here, what you can do, you can literally, start typing quantum operator, use named operators, give the matrices, or do in the shorthand representation that I'm showing you there. And by the way, as an overall effect, you can also construct one operator for the whole circuit. For example, look at here, and each operator, it has a summary box, as you can see, it tells you the dimension is, for the order, you have 1 and 2, it is a unitary. So there are lots of, interesting feature in that summary box, and much more than that. There's a long list of property. I'm going to show it to you very soon. So like any other composition, when we have a composition of functions, you can get an overall function. So you can see it as the overall function or the sequence of your operators. Which way is more interesting? It highly depends on how heavy is your numerical simulation. Sometimes if we see it as a sequence of operator, we can help you to do your computation much faster. But you can also see it as one big, quantum operator. Either way, the computation can be done. And then, it can get fancier than that. For example, look at this circuit. Let's see what we have here. We have Hadamard on the first one. We have C0 with 1 and 2. Then, this is the interesting part, our quantum framework understands lots of things that you can do with an operator. So look at here, I'm just saying that, take the square root of Pauli X. So literally that's the circuit corresponding to a square root of Pauli. So behind the scene, it's a matrix power, and then the square root of a matrix, and etc. and etc. And then for the sake of visualizations, we have lots of other options, as you can see. Let me just zoom in here. Look at the visualization. Those barriers, they are nothing but just for the sake of visualization. Some people when they are constructing their circuit, they would like to see different pieces that they have. So as you can see, that the square root, you see here, we have the square root of Pauli Z. Or after that, we have square root of swap operators. After that, as you can see here, we have a fancy rotation, a very generic rotation. We are saying that Pauli X on the first one, Pauli Y on the second one, and then each one, they are the exponential terms. This is what we usually call them as a very generic Ising type of interaction. And then after that, permutation. As you notice, we did our best to construct our framework very similar to the rest of coding in Wolfram language. It should be readable by any user. So with a very minimum quantum knowledge, you can easily read okay, this is a permutation. That permutation is between 1 and 2, and that's what's happening there. Practically every operation that you can have in quantum, we have it here. I'm just showing you another example. As you can see here, this quantum channel, that's the effect of the environment. So basically here I'm injecting noise into this circuit. This is a very special case, which is a bit flip. You can have any customized quantum channel as you like. And then at the very end, I'm just saying that do the measurement on the first and the second qubits. By convention, whenever we use double wire, it represents the classical wire. Basically, it represents your quantum measurement result. Again, remember, different frameworks, different conventions. Some frameworks, they put it on the top, some they put it at the bottom. We put it on the top. We can explain it later why, but you can customize that. Everything that you see here in terms of visualizations, coloring, fonts, everything, you can customize that as you want. And you look at that, that circuit that you see here is basically the collection of these operators. So we have quantum operator, we have quantum measurement operator, we have quantum channel. And of course, for each case, there is a reason behind this very particular heads, because we know in quantum measurement is very different from the usual operators. That's why we represent, quantum measurement by a different, function. Quantum channel is completely different animal compared to all other, operations. That's why, we have a different, function for quantum channel. So that was a very quick overview of everything. So the way that you should see it is that you have a quantum system, and then on the top of that quantum system, you would like to do a bunch of transformation. A couple of things. Look, I'm skipping a few important topics. Let me just go to the end of my representation. Behind the scene, for everything that is happening here, whenever you have a Hilbert space, you have to define your basis, and then everything is happening in a given basis. So behind the scene, most of the time, if you don't care about your basis, we are gonna make your life easy, taking care of all those basis transformation, dimensionality, and everything automatically. The only thing that you have to remember is that everything should fit. Okay, so for example, you cannot apply an operator in 3D on a qubit which is in 2D. If you do that, we will give you the error that it's not happening. So the reason that I have not started with quantum basic was that whenever we start with quantum basis, we will not have time to talk about quantum circuit, because people, they would love to see our circuits. Anyhow, so that was a very quick overview of our circuit. So behind the scene, a circuit, composition of operators. So let me just move on, focus more on operators. Whenever you think about our operators, think about two input. The first input, you are specifying the nature of your operation, is it Pauli X, is it Pauli Z, is it, I don't know, Fourier transform, is it a customized density that you would like to put it there, a customized tensor, all of that we would accept it as an argument. So you can go with the named operation, you can go with a composition of them, or you can go with something very customized. You can say, look, I would like to have my own tensor there. So as the first argument, you can put your tensor. And then the second important argument that you should remember about that operator is the order. The order tells you where that operation acts. If you do not specify that, we do it automatically. So what is that automation? We set it either as 1, 1 and 2, 1, 2, 3, basically depending on the action of your operator, we set it automatically. For example, in this case, when you are saying quantum operator acting, quantum operator without specifying the order, by default, we would say the order is on the first qubit. Okay, so we set it automatically. Or for the swap, which is an operator on 2 quantum systems, automatically we would say that, look, by definition, by default, it goes on the first and the second one. Or permutation, so by definition, we would say you are permuting the first one and the second one. You see, order, it is set automatically, okay? Let me just show you the diagram for the swap. So it's literally swap. And as you guess, it's the same as the permutation. So you can easily check. This is another interesting feature on framework. You can do all of those, comparison, testing, arithmetic that you have in, Wolfram language. You can do it on the top of our operators. Literally, you can add, for example, let's say that, you have quantum operator X, and then you would like to add it 2 times of quantum operator Z. So you can easily do it, and you are going to get a new operators. Okay, so literally any arithmetic that we have, you can apply it on the top of your operator. You can say that, look, I would like to add that with the exponential of that operator, whatever is that operation, or you can go fancy and define your rotation manually. You can say that, look, this is the of course we have the rotation, but you can also define it manually. So Pauli X is added with 2 times of rotation. And of course, everything can be done symbolic way, nothing, should be numeric. Oops. Everything can be symbolic, let me just show you what is the matrix representation of that fancy. So that's the matrix representation. Those of you who are familiar with the rotation, so that, exponential, that's contribution of, rotation, and, X and Y, it's just the factors that we added.
So if I have a pure function, I want to apply to certain.
As far as that pure function, if it makes sense, basically any function who understands what to do with the list is doable here. Whatever operation that is doable on the list, you can do it also here. Are there any question? Feel free to interrupt me. Couple of other things, why, let me just comment. I'm gonna skip through a few codes, we only have 10 minutes. So look at this construct, why I'm emphasizing, look, the order makes your life very easy, because usually whenever you want to have a complex operation, in the way that we do it in usual quantum is either a series of operation, or we create, quantum tensor product of that operations. And in our design, look at here, what I'm saying here is that Pauli X, do it on the first and the second one. So our framework automatically understands that this is the same as Pauli X on the first one, Pauli X on the second one, and using the usual, notation of quantum. This is the quantum tensor product of 2 Pauli X's. And of course, you can easily test them, and they're all the same. Okay. And again, one other reason, with the order, you can easily, the same operation, look at here, I'm just saying that, swap. With no order, it means between 1 and 2. And then for the second one, I'm saying that, swap the second one and the third one. And it understands automatically what to do with them. I already explained, the arithmetic, for example, rotation. And by the way, we also have, the rotation. You can easily test that, remember, everything is symbolic here. So it's a rotation by the angle, theta, and it's the same by Rx rotation. As I told you, like, take the square root of, like, your operators is the same as, Sx. It's just as, usual notation that we have, like, in quantum mechanics. A couple of other, comments, like, for any operation, any circuit, there are many different ways of, designing that. One way is shorthand representation. Many people, they like it because it's simple. Like, look at here. I'm saying that, look, this is a circuit operator, Pauli x on 1 and 2, and then the square root of x. There is no order, therefore it is defined as first qubit. So, and look, what's happening here. So that's exactly the operation. So x, like, basically the quantum tensor product of Pauli x on the first and the second one, and then, like, the square root of x on the third one. Let me just skip through a few of them. Like, one thing that I would like to remind you, designing control gates, very easy in our framework. And you can do it in whatever way you like. Like, look at this fancy, control gate that I have created here. You can have as many target as you like. You can have as many control as you like. And your control qubits, they can be 0 control or they can be 1 control, meaning that do the action if that, quantum system is in 0 or 1. So, and it's very easy. Those of you who are familiar with the other frameworks out there, try to create, such a gate, on those, frameworks, you would see, like, how hard it is to have this, complex control gates. There are other things, like, let me just mention, like, this very special case, like, Trotter, Suzuki, decomposition. And let me just show you the gate. Like, so this is, like, a decomposition that is very popular for time evolution, approximating time evolution. So you can easily do it in our framework. You can either do it directly because our framework, because of the symbolic, capabilities of, Wolfram language, we understand time evolution. So we can solve it numerically exactly for you, or those of you who are interested just to basically mimic the same effect using your circuit. By the way, each box is, an Ising interaction between those 2 qubits. So here I'm just using a chain of, like, 5 qubits. It's simple, but, like, then, this is the circuit, representing the corresponding time evolution. It's mostly like, taking the exponential gives you a headache. This is the method to approximate those exponentials. Last topic for today, like, we have a collection of, like, named circuits. And in particular, I would like to emphasize on Fourier transform. So basically, this is a composite transformation, basically quantum Fourier transform. And then, like, the second input is the number of qubits. So that makes your design much easier. We have phase estimation, one of the basically, the building block of, like, any circuit design. For your phase estimation, you just need to specify, like, your unitary quantum operator, and then the number of steps that you would like to basically have. If you increase the number of steps, like, your estimation will be more accurate. And of course, like, your circuit will be much more complicated. Like, here, I'm just saying that, use, 4 qubits. We have a collection of, like, some kind of textbook examples, but, like, some of them, they have more practical application. For example, like, graph circuits are very popular, especially for, measurement-based quantum operations. So whatever is your graph, you can, create the corresponding circuit. And then as the last example for today, like, a family of, like, circuits related to quantum search algorithm, Grover algorithm. So what you only need to do is just to give the input, your Boolean function, however is complicated that Boolean function, we don't care. And then you can create the corresponding Grover algorithm. There are much more detail into the Grover algorithm. Like, you can create this Boolean function oracle. You can create this phase oracle. Like, there are a lot, more detail to that. And by the way, whenever you're creating your, so after, installing the Padlet, all the documentation is there. So the same way that, like, you go to the documentation for any other, functions in Wolfram language, the same here. For example, this is the documentation for quantum circuit operator. And if you just go here, you would see all the details, like, let me just show you, like, family of, Grover search algorithm, like, phase, Boolean, and then, I don't know, amplification, or some, textbook, they call it diffusion. All of them are there. So we did our best to design our, documentation as close as possible to the rest of, like, documentation in Wolfram language. But if anything missing, let us know. I think, like, at this point, everything that you may need to do any sort of quantum computation is there. You can easily communicate with any quantum processing unit from a Wolfram notebook. So basically, in this environment, you can easily send your queries to IBM quantum systems. You can send it to any quantum computer that is available on AWS. So you just need to use, like, our Service Connect. You can get the corresponding Qiskit or Chasm, like, code for all of, like, the circuits operators. So they're all there. So in one environment, you can do whatever you want that is quantum related. So sorry, I took too long. We only have less than 3 minutes for questions. Go ahead.
Just a quick question about the Service Connect and all of that. Are there any examples?
Nick, do you mind, like, the example that you had, by the way, like, we had no time to pass it to Nick. So Nick, just upload it, or if you just send it to me, like, I'll upload it on Pathable. So there's one example, direct usage of, like, with, by the way, like, remember IBM Quantums, they are not on AWS. So for IBM is a different thing. You have to go a different trajectory, but I'll upload, like, one example for both, like AWS and also for IBM quantum computers.
I have 8 questions, but just two. So here, do you? This is the shorthand. You can add quantum operator in front of.
Oh yeah. Like, basically, like, if you want to see behind the scene, it's gonna be ugly, but, like, that's the collection of, operators defining Grover algorithm.
So my next question is more about design. This reminds me a lot of NetChain, in a sense, how NetChain could
So basically, when we were, like, focusing on, especially, maybe, Nick can comment better on that. When we were focusing on, like, visualizations for our circuit operator, we discussed a lot, regarding the things that we have in our neural nets for the visualizations and, like, the way that we constructed. Yeah, we discussed a lot when we were designing, like, these functions.
And so for when I saw the function page, I would be very interested to see, like, association, like the quantum circuit operator take association. It's not just positional, let's say, options like named arguments. You have options also.
Okay, I think we have an answer for that, but since we are running out of time, like, I can answer in more detail later, Anton. One last question. Any other question here? Okay, thanks everyone. Like, remember, like, quantum@wolfram.com, like, explore our framework and let us know if you have any feedback.